Okay, welcome all our weekly seminar at Jagiellonian. Today we have a pleasure to meet Paweł Rzążewski from Warsaw University of Technology. From my perspective, Paweł's current research focus is in the structured graph theory, with an emphasis on graph homomorphism and then specifically graph colorings. Paweł is a member of a very active and prolific Warsaw community. Over there, you have also quite decent amount of work on in the theoretical computer science and the fixed parameter tractability, or I should say in the exact algorithm. I don't know which side of this business is closer to you actually.
Rather exact algorithms.
Exact algorithms, okay. Today, what you're going to talk about today, Paweł? Tell us. Welcome.
So today's talk is about graph theory. It's purely structural one. And I'm going to talk about Treewidth of some restricted graph classes. So, okay, I hope everybody is more or less familiar with the notion of Treewidth. Should I define it? Okay, hopefully not. The problem with defining Treewidth is that if you don't know it in advance, you won't get it from the definition. But it's not that important what the definition of Treewidth is. The point is that it's some kind of a graph parameter, and when it is small, then your graph is somehow simple. And for example, if you want to do some computation, if you want to solve some problems on this graph, it's very nice if it has small Treewidth, in particular if it has constant Treewidth, because then you can solve your problems efficiently, like many natural problems. And the notion of Treewidth was, okay, actually it was reinvented by several authors independently, but one of the groups that invented Treewidth was Robertson and Seymour, who introduced this parameter in their graph minors project. And there are very many close connections between the notion of Treewidth and minors. In particular, in classes of graphs with some forbidden minors. And so far, not much could be said about other graph, like containment relations for graphs. And today I would like to focus on the relations of Treewidth and induced subgraphs. So we'll use one result, maybe I will state it now. It's a very famous theorem by Robertson and Seymour. It says that every graph, so for every k, there exists R, such that every graph G with Treewidth at least k contains R by R grid as a minor. So what is grid? You can imagine probably. It's a graph like this. And what is a minor? It says that it means that each of those vertices of the grid in your graph, it doesn't have to be a single vertex. It's just some connected set. And between those blobs, there are edges like this, and possibly many other edges, but certainly there are edges of this type. So we'll get back to this in a moment, but let's now switch to thinking about induced subgraphs. Can we say something? So, okay, in particular, if I have a graph H, I say that graph G is H3 if it doesn't contain H as an induced subgraph. So for example, if H is, say, P4, then this graph is P4 free. It doesn't contain P4 as an induced subgraph. So it's important. It contains P4s as non-induced subgraphs, but I'm insisting of having it or not having it as an induced copy. And when you ask a question like this, do H3 graphs have bounded tree? You immediately realize that it's not a good question or not an interesting question, because for example, when you take a click, then this graph is H3 for pretty much everything. For every H that is not a click, the complete graph is H3, yet it has a huge tree. So it doesn't help if you forbid anything interesting, or the same with by-click. It doesn't contain any interesting induced subgraphs, and it has a large tree. So to make this question meaningful, we need to forbid something more, or we need to assume something more about our graph. And actually, what we are going to assume that our graphs have bounded degree. So notice that if our graph is a complete graph or bi-click, to obtain large tree, you need to use vertices of large degree. So we don't have such simple counterexamples to H3 graphs of bounded degree and large tree. And today I'm going to explore this area to show you one proof and to show you a sketch of another proof and mention some results that are known. Let us start with something that is very well known, and I'm pretty sure that you have seen it. It's the class of PT3 graphs. So I'm excluding some fixed induced path on T vertices. And there is a very famous proof, and very famous, actually it's not a proof, it's a proof technique called the Jerfash path, which was invented for the first time by Jerfash, of course, to show that PT3 graphs are chi-bounded. But this is not what I'm going to focus on. So as a byproduct of this, you can prove that the treewidth of G, if G is PT3, then the treewidth is bounded by T times delta. By delta, I always denote the maximum degree. And how does the proof go? You start with an arbitrary vertex. You remove its neighbors from the graph, and the graph breaks into some connected components. So if each of those connected components is small, and by small, let's say, I say 3/4 times the number of vertices, then it's nice because we found a small separator of size delta. And for those of you who know about trees, then you know it. For those of you who don't know about trees, you have to believe it, that this is sufficient to bound the tree. So suppose that there is one large component. Then I choose arbitrary vertex here. I remove its neighborhood. And again, this large component breaks into some connected components. If they are all small, then we are done. So suppose that one of them is large, say this one. So again, I choose one guy in here. I go towards the large component. And notice that there is always only one large component, at most one large component. And I can continue this construction. And at some point, all my components will be small. But notice that what I have constructed here is an induced path, because every time I remove the neighborhood of each vertex I select. So since my graph was in the beginning was PT3, I know that this construction will stop after at most t-1 steps. So, so we have found a balanced separator of size at most t times delta. And this translates to the bound on Treewidth. If you do it a bit more carefully, you can show that the Treewidth it's not t times delta times some constant, but it's really at most t times delta. And if you do it even a bit more carefully, then you can show that even the tree depth of this graph is bounded. It's another parameter that can be much smaller than 3. Sorry, that can be much larger. But so this is a classical result, but it's not super exciting if we want to have constant tree, because if you want to use this result to show that your graph has constant tree, then your graph should be PT3 and should have constant maximum degree. But graphs which have constant maximum degree and do not contain paths, induced paths longer than a constant, have constant size. So it's not really an interesting example. But still, it's some indication that maybe something could be done here. And also, this can be interesting if you don't require that your truth is constant, because here this works for any value of delta. So this result serves very well if you want to use some kind of win-win approach to design an algorithm, because you can show that either you have a vertex of large degree, which maybe it's useful for something, or you have a small balanced separator, which is definitely useful for something. We can generalize this argument slightly for another class of graphs, and those will be C larger than T3 graphs. And I hope it's clear what this means. Those are graphs that do not contain an induced cycle of more than T vertices. So notice that if you don't have a path, then you definitely do not have a cycle. But on the other hand, you allow long paths. So this class is larger than the class of PT3 graphs. And it doesn't trivialize when you assume bounded degree. So okay, I don't say it's the most exciting class in the world, but actually in this setting, the same holds. So for these graphs, we can prove that the Treewidth is again bounded by T times delta. This is a result by Trudnowski, Pilipczuk, 2 Pilipczuks actually, and Stefan Tomasa. And let me just sketch the proof. This is not what I'm going to focus on, but I think it's also a nice argument. We do exactly the same as we did before, which means that we build a Jarfash path. So I build an induced path. I remove the neighborhood of it, and at some point, all my components will be small. The problem is that now this path can be super long. So I don't have a nice bound on the size of the separator, but here comes the twist. After I did this, as my separator, I take at most the last t vertices of this path. And I claim that after this, after I remove the red part, I mean the last t vertices of the Jarfash path and their neighborhood, every connected component is small. So let's say that there is a connected component that is large. Of course, there is at most one such component, because by large, I mean it has 3/4 times the number of vertices. So what can we say about it? First, this component certainly attaches somewhere here. And why? Because after I removed the whole path, there was no large connected component. So it must be somewhere here. On the other hand, this connected component, so actually it attaches here to this red part. On the other hand, this large component should attach here. Why? Because if it didn't, this would mean that when I was building the Jarfash path and I was considering the last vertex but one, I had no large component. So why did I make one more step? So I needed one more step. So this means that this component attaches somewhere here. And from here, I have t vertices here. And this part is connected, so I can just build a cycle of length larger than t.
Could you repeat, why do you have this edge to the left side of the red part?
Okay, so I restore, so I know that when I remove the blue part, I have no large component. And when I restore, like the prefix of this path, suddenly a large component appears. So this means that some parts that were small got merged into one big one. And the only way they could merge is by including this prefix of the path.
Okay.
Okay, so there are some technical details that I hid here. I didn't mean to make this proof super formal, because I'm actually going to prove a stronger theorem. Okay, it's maybe say incomparable, but stronger in the context that we are looking at. And the theorem I'm going to prove is as follows. So G is a C graph with degeneracy at most D. And I'm going to show that the treewidth of G is bounded by some function like this. So what is the degeneracy? You can define it in many ways, but there are two definitions that will be somehow useful for us. The first one is that every subgraph of G has a vertex of degree at most D. And another definition of degeneracy is that we can order the vertices in such a way that every vertex has at most D neighbors back. So, actually notice that we allow vertices of large degree. We don't bound the degree. We can have super large maximum degree. But still our graphs are somehow sparse. Okay, they are sparse, but it's not forced by bounding the degrees. So for example, trees have degeneracy 1, yet you can have stars that have a huge degree. The same with planar graphs.
So
They have
Paweł,
degeneracy 5.
This theorem is, I guess, still interesting if you just put the PT3 graphs, not C.
Yes, yes.
It's,
So this
okay.
this theorem, this statement isn't trivial if you exchange cycle with a path, but the form that I'm showing is stronger, as I said. This is from the paper of Gartland, Lokshtanov, Tupilipchuks, and myself. So this is the proof that I'm going to include in my talk. Let me just say one more thing that I should have said before. In general, we cannot hope to get such a statement if we don't forbid something, because you can have cubic or subcubic expanders. So those are graphs with maximum degree 3 and Treewidth, which is linear in the number of vertices. So there is no hope to bound the Treewidth just by bounding maximum degrees. You can have super large Treewidth. So we need to assume something more about our class. And what we are assuming is we are excluding induced subgraphs. Is the statement clear? Okay, so I'm going to show the proof. I'm not going to track the constants. I don't think it's so interesting.
Paweł, a question again. You mentioned tree depth before. Do you have a bound for tree depth in this statement as well?
I don't remember. Okay, let me think of it. I will get back to it later if I
Sure.
recall. And if not, I can mail you later.
Sure, sure.
Okay. Okay, anyway, sorry. So we have a graph G, which doesn't have long induced cycles, and it has degeneracy D, and it has huge tree. Okay, it's I say huge, but notice that it depends only polynomially on degeneracy. So as we think of those graphs with forbidden subgraphs, this T is a constant, it's something small, and this D is the parameter that we are interested in. So we have a polynomial dependence on this parameter. So the first tool we are going to use is a theorem by Hatzel et others, and it involves like a dual object to Treewidth, which is a bramble. So what is a bramble? It's a family of sets. It's a family of sets in your graph, such that, okay, there is, first condition is that each set is connected. And second condition is that every two sets meet. And what do I mean by this? That either there is an edge between two sets or they share a vertex. So I do not insist that those sets are disjoint. Yeah. Okay, but okay, so usually like the level of complexity of a bramble is defined in terms of the minimum hitting set. And this is okay, because if you just asked for the family of sets, since you allow them to be non-disjoint, it's very easy to construct a super large family of sets with a common with a non-empty intersection, but such families have very small heating set. So the complexity of the Bramble is measured not by the number of sets, but by the size of the minimum heating set. But I'm going to use a theorem, as I said. And what they showed is that every graph with tree at least k contains a Bramble of size. And now I'm deliberately saying size, meaning the number of sets of size roughly root k divided by polylog k and congestion 2. Okay, so what do I mean congestion 2? This means that the sets may still intersect, but each vertex can be in at most 2 sets. So in this setting, order of the Bramble, meaning the minimum heating set, is linearly dependent on the size, and I'm actually interested in the size. So we may think of this Bramble as some kind of relaxed minor. So if those sets were disjoint, we would have a clique minor. Here we have something weaker than a clique minor, but it's almost a clique minor. It's weaker because in the minor the sets are disjoint. Here I allow overlap, but this overlap is very limited. Each vertex can be in at most 2 sets. So anyway, I apply this result to my graph, and I obtain a Bramble. So B is a Bramble. So B1 to BP. Bramble of congestion 2. Okay. And P. I started with a graph with. Okay, let me just. I started with a graph with tree dt times some function of some linear function of t. Now I get roughly root of this. So my p, my parameter p is again dt to some function of t, but this function is smaller than previously. Okay, so what I do next, I make my Bramble B inclusion-wise minimal. And what do I mean by this? I look at those sets, and if there is a vertex that can be removed, and what is left is still a Bramble of size p, then I just remove it. So what happens? I will denote this Bramble by b still. So what happens after I do this? Why didn't I remove some vertex? So say I have a vertex.
But the vertex from a graph or a vertex from a set in the Bramble?
From a set in the Bramble.
Okay.
Okay. So this is my Bramble. Okay. Okay. So why wasn't this vertex removed? So there are 2 possible options. So why wasn't V moved? One option is that without this set BI has no connection to some set BJ. So maybe V is the only guy who has a neighbor in BJ, or maybe it's like this. because this vertex here is responsible for the connection. So bi minus v does not meet. So one option is that if we remove it, if we remove v, then there is some blob, some branch set in my bramble that loses the connection to v.
Wait, but if this vertex would be in the intersection, so it would be in both sets, then even if you remove it from one of the sets, assuming that they stay connected, I expect that this is your second item, but if they stay connected, then they will meet, they will still meet because there is an edge, right?
Yes.
Okay.
So the second item is that maybe it's crucial to keep the set connected. So the second option is that V is a cut vertex in the bramble. So it's not responsible for keeping the connections, but it's responsible to keep the sets connected. Okay. So let's go. So now let's prove the claim. Okay, so consider BI, which is a set of the bramble, and for all pairs of vertices in BI, the distance between U and V in G of BI is at most T. So I'm going to prove that each of those sets has small diameter. How can I prove it? Okay, so this is my BI, and I take two guys at the largest distance. So those are U and V. BI. Okay, so since I took the guys that are at largest distance, certainly they are not cut vertices. So this means that they are needed to keep some connection. So there is some BJ that only sees U. It sees U either by an edge or by containing U. And there is some BJ prime, which only sees V. But this is a bramble, so BJ sees BJ prime, so there is some path here. Maybe they share an edge like this, or they share a vertex, but certainly those vertices are disjoint. There are something more here. So if the distance between U and V was larger than T, then this whole thing gives me an induced cycle. So again, this part doesn't see anything here but U, and this doesn't see anything here by V but V, and this is the shortest path, so it's induced. So I have created an induced cycle of length at least T, larger than T actually. So I get a contradiction with my assumption. Is it clear? Okay. So notice that I told you before that brambles are almost like minors. And what I obtained now is almost a shallow minor. It's shallow, but it's almost a minor. It's so each of those branch sets is of small diameter, but it's not a minor. So the next thing I'm going to do is to turn it into a minor. So I will do a trick as follows. So I will define a new graph, G prime, and it's okay. You can define it using a lexicographic product with K2, but it's what it means if my G is some graph. Then I add a copy of each vertex. Then the copy is connected with the original vertex and the neighbors of the original vertex and the copies of neighbors of the original vertex. So I just double the graph and make all reasonable connection between the copies. So if this is X, the copy will be denoted by X prime. So what can we say about the graph G prime? It has two important properties. The first is that degeneracy of G prime is at most 2D plus 1. And you can easily see it by taking this degeneracy ordering for G. And whenever I have some X here, I insert X prime immediately after X. So now I see all my original neighbors. So this is D. I see all copies of my original neighbors. So this is the second D plus my own copy, which is plus 1. The second property is that G prime is still CT3. And notice that if we had a long cycle in G prime, then we cannot use a vertex and its copy, because if they are somewhere far away, then we got a chord. And if they are one after another, so this guy is a neighbor of him. So we'll have a chord like this. So I will work in this graph with this graph G prime. And my next claim is that G prime contains KP. P is the size of my bramble, just as a shallow minor. Depth T minor. And how do we get it? We start with our bramble. So we had our bramble B1, BP. So if it is already a minor, then we are happy, because it's all those vertices or all edges exist in my G prime. So suppose it's not a minor. Why is it? Because there is some BI here and BJ there that share a vertex. So there is some X that belongs to both. But I can easily fix it by saying, okay, so X goes to the first one, and I will, and the second, and here I put X prime. And since this X could be in at most 2 sets, it is sufficient to have one copy of my vertex X, and all the edges that were connecting any vertices to X are also connecting those vertices to X prime. And if X was the only guy who, okay, actually it was, since by the minimality, okay, maybe up to this cut vertices. Anyway, but the connection between BI and BJ that was realized by X, now it's realized by an edge between X and X prime. So with this little tweaking, we got a graph which doesn't have a long induced cycle, which has a small degeneracy, and it has a large shallow clique minor. So this is a very nice setting to work on. So the next tool we are going to use, it's something I'm not going to prove, but I will just state it. It's a classical tool used in the sparsity theory. It's okay, it's not difficult to prove, but I don't think it's worth to discuss. it says that if a graph contains KP, the T minor, then it contains Kp prime. In a moment, I will say what K prime is as mapped 3T plus 1 topological minor. So P prime is large. P prime is okay. So they satisfy that P is at least 1 plus P prime plus 1 to 2T plus 2. Okay. So as I said, I'm not going to prove it, but let's see what happens when we apply this to our setting. And also, I will just make sure that we all understand what the statement says. So by this, I obtain a topological minor of a clique. So what is a topological minor? I have some vertices that I will call roots. I have some paths between them. And actually, for every pair of vertices, I have a path because it's a clique minor. Okay, this here. I hope those are all. And it's of depth 3T plus 1, which means that each of those paths has at most 6T plus 3 vertices, I guess, I think, or maybe plus 2. Doesn't matter. It's roughly 60 vertices. So I, as you notice, I don't care about constants so much. The point is that they're short. They are of length T, roughly. And the size is chosen so that the size of my clique minor is of order d squared times t to 5th. So this is what we obtain when we put our bound on P to this proposition. Okay, so let us fix the minor model for this, and I will just try to work on this minor model to obtain a contradiction. What time is it? Okay, so let's say R is a set of roots of this, and so R is P prime of size P prime. So okay, so let's see at the graph, subgraph of G prime induced by R. It's a subgraph of G prime. G prime was of degeneracy at most 2D plus 1. So this subgraph is also of degeneracy at most D plus 1. Okay, so what does it mean? This means that we can properly color this graph with at most 2D plus 2 colors by the greedy argument, by choosing the vertex of minimum degree and leaving it for the end. So good. So what does it mean? This means that there is a set R prime, which is R, of size at least P over 2D plus 2, which is independent. I just take the largest color class. So what is this? So P prime was D squared times T to the 5th. So now I get D times T to the 5th. Okay, so let's, I have R prime and let P double prime be the size of R prime. So now my setting is that I still have a large topological minor, but now I have an additional property that the roots form an independent set. I still can have edges from roots to the paths. I can still have edges between the paths, but certainly roots are fine, are independent sets. So it's quite far of being an induced subgraph, but at least I know something about those interesting vertices. So let's H will be a subgraph of G prime, which is induced by the vertices of the minor model. So I'm looking at the graph that I have drawn on the left. So I look at it as a subgraph, induced subgraph of G prime. So, so again, H is of degeneracy at most 2D plus 1 because it's a subgraph of G prime. And okay, maybe I just this. I define a set X. This is a set of non-root vertices of H with degree at least, okay, I will just write 200 d t squared. Okay, of course, this 200 it's not that important. It's a constant. So I claim that X is small. Why is X small? Because H is sparse. Because H has degeneracy, has constant degeneracy, like or bounded degeneracy. So it has few edges, which means that there are few vertices of large degree. So what is the size of it? So let's count the number of edges. It will be the degeneracy times the number of vertices of H over something like this. So what is the number of vertices of H? It will be, okay, like this. So what is the number of vertices of H? It's the total number of vertices in all those paths. And the number of paths is P double prime of choose 2. And each of those paths is of length at most 6t plus 3. Okay, 6. Roughly 6t, doesn't matter. This plus 3 doesn't really matter.
Why do you have in the denominator 100 dt squared? What is the? It must be trivial. I just no. Well,
no. It's just I think I made a mistake because I divided by 2 because of handshaking lemma that you count edges, but I think you don't even need it.
So wait a minute. X is the number of non-root vertices of high degree, and you bound it by.
So what is the total number of edges in my graph? It's no, okay, I need it.
You need this. Yes, you need this. Yes.
Yeah.
Okay, so it's total number of vertices over the
total number of edges.
Yes. Okay.
Total number of edges over the degree, and 2 from the handshaking lemma. You're right. I need this by 2. I don't need it in the upper. Okay, good. Anyway, so let's have a look. So here I have so P double prime is let's recall P double prime P double prime was D times T to the fifth. Here I have D times T. Here I have D times T squared. So when we just simplify this, we get that this is at most 1/5T times P double prime, choose 2. And let's call this epsilon. Okay, so now I do the next step. H prime is obtained, so obtained from H by removing X and all paths that intersect X. So I have my root vertices and I didn't touch them. X is only the set of the non-root vertices. But here, okay, so here I find a vertex in X. So I remove the red vertex and also the whole path that contains this red vertex. Okay, so what is the number of paths that we removed? At most epsilon times. So actually, what we obtain this way is H prime contains T plus 1, because I didn't change the length of paths. Topological minor Z with P prime vertices. So the number of vertices of Z so this is like the minor model of Z. And at least 1 minus epsilon P double prime choose 2 edges. So now it's no longer a clique, but it's still a very dense graph. Okay, so I'm almost there. So let me just show how to get a long cycle from this, because as I said, I assumed that my graph has a large treewidth and I want to show that it has a small treewidth, so I want to find the contradiction. So okay, maybe let's go to the next page. So let's W will be a sequence. So this is a sequence of vertices from Z, chosen independently, uniformly at random, with possible repetitions. So I have my very dense graph Z, and I have those paths that realize the edges of Z, and I have selected a sequence of T half plus 1 vertices from Z in some way, in uniformly at random. So now I would like to consider, I would like to have W to satisfy 4 properties. So what are the properties? The first one is that, sorry. There's no repetitions. So the first property I would like to ensure is that all those vertices that I have chosen are pairwise distinct. The second property, I would like to ensure that every two consecutive guys, and also VT is an edge. So the next thing I would like to ensure is that this gives me a closed walk in my graph Z. And since I already assume, okay, if the first two properties are ensured, this will give me a cycle in the graph Z. The third condition I need is that for Pi and Pj, so what is Pi and Pj? Okay, so suppose that the second condition is satisfied, so the path that goes from Vi to Vi plus 1 will be denoted by Pi, conditioned that it exists. So for all two paths, if only they exist, and J, okay, maybe let's write it this way. J is not I and not I plus 1. Then internal vertices of Pi. Okay, I'm sorry. Maybe that's okay. Are non-adjacent to Vj. So again, I have a path Pi. It has Vi on one end, Vi plus 1 on the other end. So certainly this path is adjacent to those vertices, at least those two guys. But I want to ensure that there are no edges to other vertices that I have selected. And finally, the last property. Is that for Pi, Pj, their internal vertices are not adjacent. Notice that I have already ensured that the roots are non-adjacent. So the only thing I should be worried with are those. So see that if I ensure this, this means that I have, sorry, so ensuring those 4 properties is sufficient to get a long cycle. Sorry, you shouldn't write with the eraser. Okay, because I have selected those 3 vertices, I know that those paths exist by the second property. I know that there are no edges like this from here to, sorry, there are no edges like this by the third property. I know that there are no edges like this. Sorry. By the fourth property. There are possible edges like this, but it's not a problem because I can take a shortest path. I don't need to take the path Pi. I take the shortest induced subpath, and I know it has at least one vertex because the roots are non-adjacent. So if I ensure all those 4 properties, I will build a cycle which is longer than T. And this will be a contradiction because G prime didn't have such a cycle. And I will not do the calculations, but it's nothing super difficult because P1 follows from the fact that the number of vertices of Z is much larger than T, is much larger than I want to ensure. So so with large probability, I will select distinct vertices from P double prime being larger than T.
But in general, you just want to say that You can satisfy all core properties with non-zero probability, right?
Yes, this is exactly what I want. I can even just say that with large probability I satisfy all of them, but it's not important. So I can prove that each of them will be satisfied with large probability. So I can satisfy all of them. The first one follows from the fact that my ground set is much larger than I'm selecting. The second one follows from Z being super dense. So I have many edges in Z, so there is very little chance that I will select something that is not an edge. And the properties P3 and P4 follow from the fact that those paths are short and all internal vertices are of small degree, because I have removed the vertices of large degree. So each such a path excludes has very few neighbors. So there is little chance that I happen to pick one of the neighbors. So this follows from all paths being short and all internal vertices being of small. Okay, so actually, okay, so this is all. Since all those conditions, okay, actually to verify it, we need to track the constants, and the constants are chosen in such a way that those are satisfied. So since we can satisfy all of those conditions with high probability, this means that their intersection will also be met somewhere. So there is an induced cycle in my graph G prime, but we said that G prime doesn't have a long induced cycle, which is a contradiction. Okay, so let me just make some comments of this. So notice that this technique is quite robust in the sense that if I have some important places in my graph that I have already constructed, I can use this technique to fill the connections. So I can create a subdivision of some graph that I'm looking for. The limitation of this method is that we cannot branch, like at least with this method. There is no way to start even such a claw, because once we are in one of the branch sets of the bramble, we cannot guarantee that there is no triangle here. And actually, this is this is quite a serious problem in many other contexts. So in the second part of my talk, I would like to show some things related to it. I will not prove a full theorem. So if you got lost, maybe it's a good moment to get back to me. And so now I'm going to discuss this grid theorem and wall theorem. So recall we had a theorem by Robertson and Seymour, which says that if Treewidth of G is at least K, then G contains R by R grid as a minor, where quantification is that for all R there exists K. So this says that, and on the other hand, it's quite easy to observe that grid has a large tree. So this grid minor is a canonical abstraction to tree. Since we are going to talk about induced subgraphs, it's quite far away from induced subgraphs to minors. So we'll use another version of this theorem, also by Robertson and Seymour. And what they prove is that for all R, there exists K, that if the treewidth of G is at least K, then G contains R by R wall. In a moment, I will define this as a subgraph. Subgraph, not induced subgraph, but just subgraph. So what is a wall? A wall is a graph that looks like this. And what is R by R? It's the number of columns and the number of rows of this picture. And it's actually, it's fairly easy to see that grid gives us this wall, because let's recall, we have a grid which contains those blobs that are connected graphs. And there are some edges between them. So we can easily build like a subgraph, which is a wall. Okay, there is a, so this blob is connected, so there is some path here like this. Okay, here there is something like this. Then, okay, let's skip this. Okay, maybe let's make it bigger. Okay, so here I would like to, okay, I would like to build a wall. Whoa, this sounds political. So here I need to branch, but notice that if this part is connected, so there should be some vertex like this. Okay, possibly it's a triangle here, but since I'm building a graph that's of degree 3, it's easy to turn minors to subgraphs. So this is why with wall, it's equivalent if we have a wall as a minor and a wall as a subgraph. But it's still not what we want, because as you can see, we can have triangles here. Also, we can have some edges like this. So it's quite far from being an induced subgraph. So the theorem that we prove, and who is we? So this is Trudnowski. Okay, actually, the first should be Abrishami, Dibek, and myself. We prove the following theorem. So if G is STTT, in a moment I will say what it is, and bounded delta, and no line graph of a subdivision of R by R wall, then treewidth of G is at most, it's some function of T delta and R. So what is STT? It's a subdivided curve where all those paths are length T. So notice that this is precisely the structure that we are not able to build with the previous approach. We are not able to branch. Okay, it's not closely connected to what we are doing, but I think it's nice that with different techniques we can build different things. It's not so clear how to merge those techniques to do something more general, but still we can do something in this setting. Notice that again we have a subdivision here. We have this STTT3, but again, notice that if I exclude this, I also exclude subdivisions of this, because I have a subdivision of this if and only if I have a subdivision of this. And if you recall from the first part of my talk, the classes that I was considering were PT3 graphs, where excluding a fixed path is equivalent to excluding a subdivision, every subdivision of this path. And I was also excluding long cycles, and it's equivalent to excluding all subdivisions of a cycle.
Paweł, just to go over the assumptions, so no STT is an induced subgraph, bounded
Yes.
degree, and what is the third one? No.
Bounded degree, no, sorry, a subdivision of.
Because the
It's
induced.
Yeah,
Oh,
sorry. Yeah, this is like that's the main result. Sorry.
Okay.
Thank you very much.
Okay.
That's the main result. So this is we are able to. We have this like wall theorem which talks about graphs, and here we are able to prove some variant of induced wall theorem. It's not wall; it's a line graph of a wall. But it's induced. So, like, thank you. This is that's actually what makes this interesting. And what is the sketch of the proof? I will not prove it, but I will just show you the point where we go from subgraphs to induced subgraphs. So I think it's an interesting trick. So the first, we consider our graph, which is STT3 bounded delta, and it has large tree. So say we go for contradiction and we assume that our graph has large tree. So the first part of the proof, and that's something I'm not going to show how to do. It's quite a lot of work. We show that there is G prime, which is an induced subgraph of G, which has which is claw-free and has large tree. So somehow we go from excluding a long claw to excluding just a claw, and by claw I mean, of course, just this. So the next part of the proof. So, okay, why are we happy about this? Because the structure of claw-free graphs is quite well understood, and there is a series of papers, in particular by Trudnowski and Seymour. And we use one of them, like the fifth, claw-free graphs 5, to obtain that there is some graph H such that G prime is, okay, here I'm not going to define it, but say it's almost the line graph of a subdivision page. It's so formally they provide some kind of a decomposition of this graph. They call strip decomposition, but on the high level, it means that G prime behaves like a line graph of some graph. Okay, so now, and it's also H is of bounded degree. It follows from the fact that the G prime is of bounded degree. So the next step, so there is a theorem by Harvey and Reed that the treewidth of a line graph is at most delta times treewidth of G. Maybe there is some constant here involved, but it's so notice, if G prime is the line graph of H, H has bounded degree. So this means that H should have large tree, because if H had small tree, then G prime would have small tree. So H has large tree. Okay, I'm running out of space, but let's just write that G prime is an induced subgraph of G. G prime is almost a line graph of H, and H has large tree. So this is what we know so far. So we apply the wall theorem to H. So we know that H contains a subdivision of the wall as a subgraph. But now let's get back to G prime. So what does it tell us? So G prime is the line graph of H. So G prime, so if H contains a subdivision of the wall, then G prime contains the line graph of the subdivision of the wall. But notice what happened. Here in H, I have a subgraph, which means that I'm allowed to remove some edges. But G prime is the line graph of H. So removing edges in H corresponds to removing vertices from G prime. So this is where I go from subgraph of H to the induced subgraph of G prime. So G prime contains a subdivision. No, not a subdivision, the line graph of the subdivision, this way. A line graph of a subdivision of wall as an induced subgraph. Yeah, so I think this is a cute trick to go to the line graph, because this allows us to switch from graphs to induced subgraphs. Okay, I have just one last thing to say. So actually, we were able to prove something stronger, meaning that we exclude something less than this long claw. But like the ultimate goal in this area of research, and we are very far from it, is the conjecture. It's a conjecture of Abulker, Adler, Kim, Cintiari, and Trottignon. And they conjecture as follows: every bounded degree graph of large tree contains as an induced subgraph a subdivision of the wall or the line graph of the subdivision of the wall. Subdivision of the wall. So
I guess it's critical to have a vision. What is the line graph of a subdivision of the wall? It's just a wall with the triangles.
Yes. That's I was going to
instead of the pegs, right?
Yep.
And I guess you don't really have a wall as an induced subgraph there, right? You cannot find it. These triangles kill you. That's why you.
Yes. That's why. Yes. So I have some connection. Yeah. In some places I will have triangles. In some places I won't have triangles, and I take the majority and I create one of those two structures. Yes, that's precisely what happens. So here we very conveniently notice that if I have a wall, I'm running out of space, then this wall contains a long claw. So we simplified our problem by excluding a long claw instead of the full wall. But somehow we reached the second statement. As I said, we have slightly stronger results, but they are of similar nature. We don't exclude the wall, but we can exclude something more complicated than just a long claw. So yeah, so this is what I would like to conclude with. I think it's a nice world. Most of the results the results I was presenting are very fresh, and most of the references are rather fresh. So there is pretty much to do. And let me advertise one more thing. I started with saying that we exclude some fixed graph and we have H3 graphs. But actually, as I already pointed out, in all cases, I was actually excluding all subdivisions of my graph. Or if I said that I exclude a specific graph, it was equivalent to excluding the subdivisions. So I think the world of H subdivision free graphs is also a very nice setting, and there is not much done here. So if you have some favorite results about classes with forbidden subgraphs or forbidden minors, you can ask about forbidding like induced topological minors, which is equivalent to excluding induced subdivisions. So let me finish with this.